All right. What is a reasonable estimate of the volume of an adult person? Okay. So let's get an adult person over here. All right. Right. Okay. So let's just say it's me. Better, right? Okay, let's just say this is me. I'm 6 feet tall, right? And I'm, like kind of the Western average, I guess. The Western average, okay, I'm 6 feet tall. That's 1.8 meters, right? 1.83. Well, let's go with 1.8, right? So what I'm trying to do is essentially encase myself in a box which would have the same volume as me. The box is much bigger, but at least we'll know what the maximum it could be, right? So what would this box, what would these dimensions be? Okay, just a bit neater, I guess. Kind of like that. That would have been better. All right, well, the height of this box is 1.8. What's the thickness of this box? I'm gonna say from here to here. So I'm just gonna ballpark it. I think I can use those small rulers, which are 15 centimeter. Two of those, slightly more, and I'm on the thinner side, so I'll use just the slightly more. I'll use 40 centimeters, which is 0.4 meters in breadth, I guess, and in depth. What's that going to be? I'm having a, I think this is going to be much less. What can I go for? Very little idea. Sorry, excuse me. Go with 25 centimeters. Right, so 25 centimeter, which is 0.25. So multiplying this, calculating the volume of this, I'm getting 0.18 meter cube. Now there's a lot of empty space over here, right? So I'm gonna suppose, like, what do you guys think? I'll say there's 30% free space, relatively, maybe 40%. I don't know. So the volume of the box is much higher than the volume of the person inside, me inside it. So I'm gonna be like much less. So I'm gonna be close to maybe 1 point. I don't know. I'm not even calculating. Less, right? 1.5, 1 point, I don't know, 2.5. So somewhere around here is my best guess. And I'm just calculating it for myself. I'm 6 feet tall, pretty thin. So that's my best guess, right? It can't be that high, right? That's 5 times, not five, but like 2 or 3 times. So that's not the average guy. That's like a pretty bulky guy. If it was like, two, maybe I'd consider, not even two, because there's so much empty space, and go for somewhere close to this value. The only value that's making me happy is A. So I'm going to be confident A is the answer. Which combination of units could be used for expressing the power dissipated in a resistor? Power, I can't think of anything, but work is joule, and work is force times distance, so Newton meter, right? So Newton meter per second makes a lot. Oh, it's already here. Newton meter per second for power makes a lot of sense to me. All right, that's I guess I was thinking in the same lines as the examiner. D is our answer. In this question, we just have to resolve the forces. So let's resolve this one, all of them, in horizontal and vertical. So the horizontal component, net horizontal component is, well, this angle is going to be 30. So it's 10 cos 30. But there's also 5 in the same plane, -5. That's matching one of our answers. And this is just going to be 10 sine of 30, right? So let's see if that's a pair. 10 cos 30 with the 10, no, not cos again. Yeah. 10 5 sine, not 5 sine. I'm looking for 10 cos 30 minus 5. 10 sine 30. What is this? 10. I don't see it. I do not see it. Maybe they've done it some other way. How have they done it? Maybe they've tried to resolve this like this. Okay, let's try doing that. That's super weird. I guess they're trying to confuse us. Okay. It just needs to be resolved. So they're taking their frame of reference as this being the x, right? Poorly drawn, but let me just extend this part. This would be 30. So this is 5 cos 30. And this angle would be not drawn properly, but 5 sine 30. And this is going to be minus 10. Or it could be 10 minus 5 cos. I don't know which way. I guess 10 minus 5 cos 30 makes more sense, because 10 is the larger value. 5 cos 30 is going to be smaller than 10. So it's going to be 10 minus 5 cos 30 degrees and 5 sine 30. Is that 5 sine 30 is here, 5 cos. Okay, I think C is our answer. Let me double check. 5 sine 30, 10 minus 5. And I only switched it from here because I recalled while working that there was only some value minus another value. So I just flipped it. There was no minus 10 over here. So it was just larger value minus smaller value. It doesn't matter as long as the net result is the same. If like the magnitude with this or this will be the same, the direction will be different, right? So C is our answer. Right, so the signal frequency over here is 25 hertz. It's displayed on the screen. If the frequency is this, the time period for this wave is going to be 1 over 25, which comes out to be 40 milliseconds, right? And this length is going to be half of that. So our answer just becomes B. Very straightforward. B. So it's talking about speed. So that's just the magnitude of the velocity. So what's going to happen is there are two components of the velocity of this projectile, the vertical component and the horizontal component. The horizontal component will stay constant, right? And the vertical component will be a maximum when it starts, be a minimum over here because it stops moving vertically, then falling down. So it's going to come down then, right? So it's going to be, like the graph is going to be like this, right? Maximum when it's shot up, maximum. And these are velocities. So it's going to be, so these are, this is speed, but if it was velocity, it would kind of reflect like that, but because it's negative now, right? But that doesn't matter for us right now, so I'll just erase that part, right? And because there's always a constant added, it'll always have some velocity. The zero line will not be here. It won't go like that. It'll be slightly lower because it has some base value all the time. So something like that would be the graph, and C looks like a really good answer. C. Our answer is C. I'm redoing this question because instead of taking acceleration as 0.2, I took it as 2. So I made a typo. But essentially, a train is initially at rest and has uniform acceleration 0.2 until it reaches a speed of 20 meters per second. It travels for a time. So essentially, I want to work on the graph, the velocity time graph. Journey ends over here, maximum velocity here. So it's gonna go up like that. And the deceleration is larger, so it's a steeper down and something like that, right? This is 20. So I'm and my idea is I can figure out the distance traveled here, over here, and the time, right? By simple maths, and then figure this out by the end. So let's figure out A, B right here, B, and then C, right? So the math for A is going to be just V equals to U plus AT. Velocity is, final is 20. Initial is 0 plus 0. This is the mistake I made. I took 2 instead of 0.2. I could have just divided it by 10 then. Oh well. So the time it took was 200, what? 20 divided 100 seconds. 100 seconds. So I'm rooting towards D or C already because the value is so high. So this is 100 seconds. Let's figure this out. For B, the velocity, still same equation, V equals to U plus AT. This time around we know that the final velocity is 0. This is going to be initial velocity 20, and this is minus 0.4 t. So that's 20 divided by 0.4, and I get 50. So this length is 50 seconds, right? This length is 50, right? Now I have to figure this out. One thing I can also do is quickly figure out the area, which will give me the distance, the area over here, which is 20 times 100 divided by 2. So that's just 1,000. And over here it's 50 times 20 divided by 2, which is 500. Interesting. So this area is 150 because the distance traveled is 150, right? And the height over here is 20. I can figure out the length, or essentially the time. So that's going to be 150 divided by 20, 75. This length is 75. Total journey is 75 plus 50 plus 100, 225. Wow. Look at that. Exact answer. I love it. I think I spent a little extra time. Maybe there's a faster way, but I was focusing less on calculating, less on solving the problem quickly, more on explaining the graph over here. A roll of tape of length 50 centimeter required a constant force of 20 to unwrap it. What is the work done in unwrapping it? The work done is, so in other words, what essentially you're doing is you're using, what is the work done by you? Not on the tape, but by you. So you're pulling something with a force of 20 at a particular distance until the tape runs out. So you're pushing it, pulling it, whatever, the force of 20 until 50 meters go by, or 50 meters. That's just 1,000 newtons. So I think straightforward question. D is our answer. All right. A trolley of mass 600 kilograms is initially at a point P of a slope at a height of 80 meters above the ground level. As shown, the trolley is released from rest and moves along the slope. First comes to rest at point Q, the height h above the ground level. So right? This happened because there was a lot of energy loss because of friction, and they're saying the work done against friction is this much. So 1.5 kilometers, there was a force of 30 newtons opposing the motion of the trolley as it moved down the slope, or total journey down the slope. So what if there was no friction? How would this path look like? Well, the trolley would have ended up somewhere on the left hand side, which I don't have access to, but at a height of 80 again. If all the kinetic energy was converted to gravitational potential energy again, right? So this would have been 80. So this from over here, from the top of H where it stopped, from here all the way till here, is actually the energy lost, or the work done against energy lost, right? Or the work done against the trolley, because it lost all of that work. That's how it lost it. So that is essentially the friction forces, which is the work done is F times T. So let's calculate it once we know that. So the total energy is going to be, let's make some room. So the total energy is gravitational potential energy, or when it started at start, is equal to mgh, right? And h is just going to be 80, right? So I'm not going to put m in. I'm thinking it's going to get cancelled out, right? And at the end, the gravitational potential energy is just going to be mgh, right? At the end, with h as the value. So the force, so what am I trying to do here? So I'm trying to say the start gravitational potential energy is equal to, that's what I drew earlier, right? The start is equal to the end gravitational potential energy, the energy here, the mgh, and the energy lost. That's what I wrote. Energy lost plus these two, right? So at start, I've said it's going to be 80 mg. Energy lost was F times D, which was 300 times the distance, which was 1500. I think I'll have to put mg in there. And at the end, it's just going to be mgh. Let's make some more room. Right. So, all right. At least I wish I could have taken out g. But I think I can simplify it. At least, yeah, I can. Let's try that. Let's commit to our complicated way of solving. I am committed. Instead of putting in the values, I'll try to do it without the values. Let's see if I can. 80 mg. So if I take mg common and bring these two sides to the same side, this is going to be subtracting. So mg is the common thing. It's going to be 80 minus h equal to 300 times 1500. 300 times 1500, which is 450 kilos. I have to put it in, don't I? The weight of the trolley. Do I have the question open? The weight of the trolley. I'll have to check again. Going back, I'm seeing the weight of the trolley is, I think, 600. The mass, sorry. So it's 600, so essentially 4,500 divided by 6,000. Divide this by 6,000 is 80 minus h. And h comes out to be 15, I think. 15 meters. No, 5 meters. What? 5 meters, sorry. It's coming out to 5 meters. Yeah, alright. 5 meters, and yeah, the reason I'm getting 5 meters is if I took g as, I took it as 10, it's giving me a drastic different value. I'm surprised. But if I took it as 9.81, I would get somewhere close to 3.6 meters, and the answer would then be A. And the thing is, I'd be confident with that answer even without double checking it, because I just looked at the options again, and A was 3.5 and B is 76, then we have 79 and 80. So I think we know what we're doing. Why is 80, 79 and 76 the answers? Those are drastically different values just looking at the diagram. So they're hinting at, because it's less than 40 definitely, just by looking at the diagram. Oh well, let's move on. A straightforward question. The force being used from our, this is the force being applied, but the force being used to move and do any work is actually 12 cosine of 30. And well, if you want to calculate the power, that's going to be power is equal to the force, which is 12 cosine 30 times 2, the velocity, and we'll just get 20.79, I think, meter, not meter, watts. And the answer B looks very appealing. All right, I'm not a fan of this question because it's kind of sad, because what they've done is they've switched the values. Essentially C is the answer because the area under the graph where the limit of proportionality stops behaving as a elastic material. The area underneath would be the plastic deformation, but it's you don't see force over here, but it's essentially this graph, but with a different area highlighted. So this area, essentially it would be very similar to this if force was here and E was over here, but they haven't done that. Sad, but yeah, I don't know why they did that. C is the answer.